Okay, welcome to the Electronic Healthcare Record Challenges session. My name is Justin Ganay at Sage Bionetworks. And in this session, we'll be discussing the patient mortality challenge as well as the COVID-19 challenge. These challenges were made possible by support from the Center for Data to Health. This is a program to support informatics across the Clinical and Translational Science Awards program. This challenge was also made possible by collaboration with the University of Washington Medical Center and Sage Bionetworks. And I would like to specifically thank Sean Mooney at University of Washington, who's been a real champion for this challenge and had a true vision for reimagining access and use of highly sensitive EHR data to advance predictive analytics and to improve patient care. And I see this challenge as a bold first step in the direction of clinical benchmarking for AI. We'll start with a presentation from Tim Bergquist and Tomas Schaffter. Tim Bergquist is a graduate student at the University of Washington, who I'm pleased to say has recently joined Sage Bionetworks as a research scientist, and Tomas Schaffter is also a research scientist at Sage Bionetworks. And this will be followed by a presentation from the top performing team, Jafone Go, at the University of Wisconsin. So without further ado, pass it over to Tim and Tomas.
So hi, my name is Tomas Schaffter, working at Sage Bionetwork, and today I will present the organization of the results of the First EHR DREAM challenge, titled Patient Mortality Prediction. So this challenge was organized by the University of Washington, who provided the EHR data, and Sage Bionetwork, who provided the expertise in terms of infrastructure to process the EHR models that you have received. This challenge was also supported by the National Center for Data to Health and NCAT, who provided server to evaluate the performance of models. So the vision that we have is to develop an ecosystem for unbiased assessment of clinical models on EHR data. So the idea is for researchers who develop their model to be able to submit it once, and then the ecosystem would automatically send this model to different data sites over the US, where the model would be evaluated independently. And then the results of the model on each data set from these data sites would be collected and then returned to the participants. So the question that we asked in this challenge was, given all the electronic health record of a patient, try to predict whether this patient is going to pass away within 6 months after the last available exam. So here you have a representation of the model submitted for evaluation. And what this model took as input is a collection of EHR data, so electronic health record for a given patient. And then what we ask is the algorithms to output a number between 0 and 1. 1 being that meaning that the algorithm is sure that the person is going to pass away within 6 months after the last exam, and 0 meaning that the person will not die. So in this challenge, we used 10 years worth of data. So that's EHR data collected between 2009 and 2019. This represents 1.3 million of patients with at least one visit. And just to give you a few numbers, so this captures 5 million drug exposures, 10 million observation, 48 million condition, and 221 million measurements. And so this data that we provided as input to the EHR models were formatted according to the OMOP common data model. So for the need of this challenge, we developed an IT infrastructure, which we called model to data approach. So in this infrastructure, you have a developer who is developing locally a model, potentially using private EHR data. In the case of this challenge, we provided a synthetic data set that does not include meaningful information, but was providing to the developer an example of the format of the data that we were using in this infrastructure. And so the developer would build the model locally, and then he would submit this model to Synapse. that is a platform developed by Sage Bionetwork. And we use this platform to host the documentation of the challenge. So it's documentation about the data format, how to prepare a submission, and how to send it. This space also provided the developer with a dashboard where he can track the progress of his or her submission, a leaderboard table to compare the performance with the performance of the model of other developers, as well as a space where the developer could discuss among themselves, as well as discuss with the organizer of the challenge. And so the way it works is that once the developer have submitted their Dockerized model, the model was sent to an NCAT server for validation. So on this server, we used synthetic data that did not contain any PHI, but we were able to use this data to train the model, to run the training program of the model, and then later run the inference program of this submission. And then as the output, we obtained a prediction file. And then we performed some checks. For example, we tested that all the patients included in the data set had a prediction in this prediction file. We also performed other validation, such as we evaluated the runtime of the algorithms, and we applied a cutoff so that once we apply the model on the entire EHR data at UW, which is several times bigger, we know that the model is not going to take longer than a couple of days. And so because we were using here synthetic data with no PHI, in this case, we were free to return to the participant any log file or output files, so that in the event of an error, the developer can troubleshoot his model. If the model passes this validation stage, then the model is automatically shipped to UW Medicine server, where the real EHR data are. And so the only thing that goes inside this very secure network is the model submitted. And so here again, we go through the process of training the model by running their training program, which output a trained model. And then the trained model is fed as input to the inference program. And then the inference program is used to generate prediction about for patients in an evaluation set. And then we evaluated the performance of this prediction, which is actually the area under the row curve and area under the precision recall curve. And the only bit of information that left this secure environment are these two performance metrics, which were then returned to the participant. So this is a traditional challenge timeline of a DREAM challenge. So we started with a pre-registration phase and open phase, and then we had a leaderboard phase divided into 3 rounds. And in each of these rounds that lasted about a month, developers were able to submit up to 3 times. And so in this leaderboard phase, we used data collected between 2009 and 2018. And because we wanted to evaluate model in a prospective manner, then we took the model and evaluated them on an unseen data set that was composed of data from 2019.
Thank you, Tomas. My name is Tim Bergquist, and I'm a PhD candidate at the University of Washington and a research scientist at Sage Bionetworks, and I'll be presenting the results of these challenges. So as Tomas mentioned, there were 2 rounds, the leaderboard phase and the validation phase, in which we allowed participants to build models on our electronic health record data at UW. So participants were allowed a grand total of 11 valid model runs, or valid model training and evaluation. And so these are the final results for the leaderboard phase. So at the end of this period, we had 14 models that all scored over 0.9 AUROC, area under the recall curve, and the top 4 models all scored over 0.2 area under the precision recall curve. The way we scored this challenge was that the area under the recall curve was the primary metric, and then the area under the precision recall curve was the tie-breaking metric. So if we decided that there was not a significant difference between the 2 AUROCs, we would then turn to the AUPR as the tiebreaker. So here you're seeing the top 14 or top 13 teams. But then we took after the leaderboard phase was done, we had one more final submission from each team that we then evaluated against this future data set, the validation data that Tomas mentioned in the timeline slide, where we pulled patients who appeared at UW during 2019, and we took all of their data and we evaluated models against those to see how well a trained model would prospectively be evaluated on a live new incoming data. So the results of the validation phase were that only, if you remember, the top 14 had over 0.9 AUROC. During the validation phase, only 3 people stayed above 0.9. Everyone else dropped drastically to 0.8 all the way down to 0.7. And you can see I'm highlighting here the top 5 teams, and there's their corresponding lines in the area under the recall curve and the precision recall curve. So this is just showing the decrease between the leaderboard phase scores and the validation phase scores. And really the top 5 teams who are in the top 5 for the validation phase were not in the top 5 for the leaderboard phase. And they just were able to build models that generalized better to a future data set. Specifically here at the top was UW Biostats, and I'll talk a little bit about their model here. So the top team was UW Biostats, and this is not University of Washington. This is the University of Wisconsin Medical System biostatistics team, and they built a model that was pretty cool. They had they did a light gradient boosting method where they used 1,400 features that had non-zero weights, but each of these features incorporated over 1 million unique concepts that were in UW's data. And the way they incorporated them is that these features are part of what are biomedical ontologies, things like SNOMED or ICD-9, where you have granular concepts at the bottom of these hierarchies that are children to parent codes that are more and more, that are broader and broader in clinical categories. And so they used a roll-up algorithm where they took these low-level concepts and rolled them into higher level clinical concepts and used those as their features. So they took over 1 million, rolled them up into 1,400. And they also used measurement values. And so you can see in the top 5 features here on the right, of the top 5, 4 are actually explicit measurement values. So the average pulse of a patient over the past 6 months, the average diastolic blood pressure over the past 6 months, average systolic, and then also the latest systolic blood pressure measurement in a patient's record at the time of prediction. And they had an interesting way of training their model. So rather than taking all the historic data we made available to them, they upweighted the more recent patients in the data set to make their model more fit to the more recent data. EHR data can change a lot over time. There's a lot of concept drift that can happen. And so doing so seemed to make their model more robust to future change. So between incorporating over 1 million features and upweighting more recent patients, they were able to generalize better to future data sets. So after the validation phase, we took a deeper dive into the performances of these different models. One of the more relevant topics today is the impact of racial bias on in machine learning. And so we wanted to take a look at how models performed across different demographic variables. We have to move beyond this idea that models should only have one score or one metric. And so we wanted to take a deeper dive into these. And here's just a few papers kind of highlighting this problem. So what you're looking at here is the Bootstrap distribution of the top 10 models broken down by race. And we're looking at how they perform across each of these 4 race groups. So we looked at white, Asians, Blacks, and other. And so what you can see is across the board, models perform, there's a lot of evidence that models perform better on the Asian population than on the other groups of patients. And the heat plots you see on the right here are the comparison between 2 racial groups. So if you look at UW Biostats and we see the Asian group, you can compare that along the line to all the other cross references to each of the other racial groups. So the first square there that's red is comparing whites and Asians. And so the red just means that there's a lot of evidence to suggest that the Asian population has higher accuracies with UW Biostats models. The other interesting thing to look at is when we compare across methods, how models perform across different racial groups. So if we look at ProActa and PNP India, when we look at the high level category, the high level score of Proactive's model, they perform better than PNP India. However, when we look at PNP India and how they perform on the Black population versus Proactive's performance on Black population, there's actually a shift. And PNP India is more accurate on the Black population than Proactive is. And this is super interesting because these are trained on the same data and they're evaluated on the same data. And yet we're seeing this shift across the board. So anyway, so yeah, we have to be considering these sort of things as we're building clinical prediction models, and especially as we implement them and have them output predictions to doctors, we need to be thinking about this sort of thing. The other thing I want to bring attention to is we asked participants to make predictions from their last visit, and we wanted to see if the type of last visit had different accuracies. So we looked at whether the last visit was an outpatient visit, meaning a patient went into the clinic and did not stay overnight, whether a patient was an inpatient visit, whether they went in and stayed overnight, or whether they went to the emergency room. And there's wide variations in accuracies across these different clinical contexts. And we just need to be thinking about, for future DREAM challenges, we need to ask more context-dependent questions, because if we look at, say, Ultraman God's model, he performs really, really well on inpatient visits, better than anyone else outside of the top 2 teams, but very poorly on outpatient and emergency room visits, and other models do better on those. So we need to be thinking about asking more clinically or contextually dependent clinical prediction models. So in conclusion, the model to data approach allows intelligent feature engineering and model development while keeping private data private and secret. Models can vary in their performance across sensitive demographic variables, and we need to be keeping that in account as we evaluate these models and implement them into clinical practice. And future EHR DREAM challenges should focus on context-dependent questions, keeping in mind where they'll be used within a clinical workflow. And also we should be focusing on clinically actionable questions, things that doctors can actually, where the predictions are actually actionable for physicians to prescribe treatments on. And I also want to pitch the EHR DREAM Challenge COVID-19. We've taken this model to data approach using UW's electronic health record data, and we've spun off a few more interesting prediction questions that we're asking around COVID-19. So check out that link, and thank you so much for your attention, and we can take your questions now.